Hello students, welcome to Memo Neet. This is Ravikant, the physics teacher, and today I'm going to continue with the ray optics. In the first part of this ray optics, we have seen reflection of light and the two reflection from the spherical surfaces, right? I hope you all understood the things and commented the relative things in the comment box. The comments will be seen and that will be the things which is being mentioned over there will be taken care of, right? And today in this lecture we will be discussing about refraction of light, right? Refraction of light and refraction through prism. So what is refraction of light? See, refraction of light is the case when the light ray is traveling from one medium to another. So if there are two different media, then let this be the line. If this, let consider this line. Now this line is separating medium 1 and medium 2, and therefore this line is known as interface, right? This is no actual line, it's just an imaginary line, just to make a clarity that beyond this line, above this line is medium 1 and below this line is medium 2. Now what happens in refraction is that a light ray gets incident at a point on this interface, right? Now this light ray is willing to travel beyond this interface. So it would had traveled along this straight path, but because the medium is changing, what happens because of the change in the medium, the speed of the light ray changes, and because the speed of the light ray changes, it bends from its actual path. So if I draw a line which is perpendicular to the interface, then this line will be known as normal, as we saw in reflection also. So this is normal, and this angle between incident ray and normal is angle of incident I, right? Now this dotted line would have been the actual path of the light ray, but because it is moving from one medium to another, the speed of the light is changing, and as the speed of the light is changing, the light ray will bend from its actual path. So it has two options to bend. Either it will bend towards the normal and follow this path, or it may bend away from the normal and follow this path, right? In both the cases, the angle between the normal and the reflected ray, either this or this, will be the angle of reflection, depending on both of the rays cannot be present at the same time, right? Either this reflected ray will be there or this reflected ray will be there. That is, either the light ray will bend away from the normal or it will bend towards the normal, depending upon the speed. How it bends away from the normal and how it bends towards the normal, that will be discussed later. But what the thing which we need to understand over here is, or what I want to convey over here is, what is reflection, why reflection occurs. Reflection is the phenomena in which the light ray refraction is the phenomena in which the light ray travels from one medium to another, and while traveling from one medium to another, it undergoes bending of its path. That is, it bends from its original path, and this bending occurs because of the change in the speed of the light in two different mediums, right? Now, why the speed changes? The speed changes because of change in the optical density. What is optical density? See, optical density is defined for a medium. A medium is said to be a denser medium or a rarer medium if a medium, in comparison to some another medium, the velocity of the light in that particular medium is less, then that medium is known as a denser medium. Suppose we take two mediums, medium A and medium B, right? The speed of light in medium A is let's say greater than speed of light in medium B. For this case, medium A will be known as a rarer medium, that is its optical density is less, and medium B will be known as a denser medium, that is its optical density is more, right? For a case when velocity of light in medium A is less than velocity of light in medium B, for that case, medium A will be known as a denser medium and medium B will be known as rarer medium, right? So defining optical density could be done only if we are comparing two different mediums, right? And the rarest medium is vacuum. Rarest medium is vacuum, or you can say free space or air. So if rarest medium is vacuum, then if you compare any other medium with air, any other medium would definitely be a denser medium. So what I want to say from here is that the speed of light is maximum in vacuum or air. That is, the speed of light in vacuum or air is given as c, and c is equals to 3 into 10 to the power of 8 meter per second. 3 into 10 to the power of 8 meter per second. This is the speed of light in vacuum or free space or air, right? And this is the maximum speed, right? This is the maximum speed. Therefore, we say that air or vacuum is the rarest medium. There cannot be any other medium which is rarer than air or vacuum. So any other medium besides air or vacuum is a denser medium. That is, the speed of light in any other medium besides air and vacuum will be more less than the speed of light in air or vacuum. Right? I repeat, the speed of light in any other medium would be less than the speed of light in air or vacuum, right? So when we compare two different medium, their optical density is being defined on the basis of the speed in the two medium. If the speed of light in one medium is less as compared to the other, then the first medium is a denser medium and other medium is the rarer medium, right? So when a light ray is moving from denser to rarer, whenever during refraction a light ray is moving from denser medium to rarer medium, what will happen? The light ray will bend away from the normal. From the normal, right? And if it is the case when the light ray is traveling from rarer to denser, then the light ray will bend towards the normal, right? Light ray will bend towards the normal. So this was the case which I discussed in the beginning, that light ray while moving from one medium to another can bend either towards the normal or can bend away from the normal. So it will bend towards the normal if it light ray is moving from a denser medium, so from a rarer medium to a denser medium, it will bend towards the normal. And if it is moving from a denser medium, if it is moving from a denser medium to rarer medium, it will bend away from the normal. And if it is moving from rarer medium to denser medium, it will bend towards the normal, right? Denser medium is a medium in which the speed of light is less as compared to some other medium, and the rarer medium is the medium in which the speed of light is more as compared to some other medium, right? Is that clear? Now let's talk about the laws of refraction. So laws of refraction. What laws of refraction say? The first thing it says that the incident ray, the reflected ray, and the normal, all the three rays lie on the same plane. The second thing it says that sine of incident ray upon sine of refracted ray is always constant. That is, this ratio is always constant for a given pair of medium, a given pair of medium, right? That is, suppose we have two medium. Here we have glass and here we have water. So for glass and water, if the light ray is getting refracted, this is angle of incidence. If light ray is getting refracted, now glass is a denser medium, water is a rarer medium, so light ray will bend away from the normal, and this will be the angle of refraction, right? So here sine I upon sine r, let's take just for an example, let's say is equals to x. So this x will always remain constant, that is whenever there is refraction between glass and water, the angle between I sine I upon sine r will always be x irrespective of the values of r. Means if I increase the value of I, value of r will be so adjusted that sine I upon sine I r always remains equals to x, that this ratio will remain constant. That is, if I change angle of incidence, angle of refraction will also change accordingly, right? This what is known as the second law of refraction, and this law is known as Snell's law. Snell's law, right? So what Snell's law says that the sine I upon sine r for a given pair of a medium in case of refraction is always constant. Now what is this constant? So sine I upon sine r is always equals to velocity of light in medium 1 upon velocity of light in medium 2. When I say medium 1 in throughout in this lecture, medium 1 will always mean the medium in which the medium which contains angle of incidence, right? The medium which contains angle of incidence will be taken as medium 1, and the medium which contains angle of refraction will be taken as medium 2, right? So sine I upon sine r is constant according to Snell's law, and that is numerically equal to the ratio of the velocity in the first medium upon velocity in the second medium, right? And this quantity is given as name of refractive index. Refractive index, right? Refractive index, and it is represented by mu and is written as refractive index of second medium with respect to first, right? How we read this? We read this as refractive index of second medium with respect to first, right? With respect to first means this is the refractive index of the medium which has the refracted angle with respect to the medium which has the incidence angle, right? I hope this is clear. So sine I upon sine r is a constant, and what is that constant? That constant is the ratio of the velocity of light in first medium to the velocity of light in the second medium, where when I say first medium means the medium containing the angle of incidence, and medium 2 means the medium containing the angle of refraction. And this ratio is known as refractive index, and which has been represented by mu. In some books it might be represented by small n, right? And this is what is known as refractive index, and this refractive index is written as refractive index 1 2, which is read as refractive index of second medium with respect to the first medium, right? With respect to the first medium, this is what is refractive index is. Now if I say that we fix one thing, what we fix, that medium 1 is air, medium 1 is air, then medium 2 may be any other medium, and velocity of light is maximum in air. So refractive index of some medium, I'm writing it as M, refractive index of some medium with respect to air will be equals to speed of light in air upon speed of light in that particular medium, right? Suppose, just for an example, if I say if medium 2 is glass, right? Let's say it's glass. Now, if medium 2 is glass, then I will say refractive index of glass with respect to air is equals to velocity of light in air upon velocity of light in glass, right? Velocity of light in air upon velocity of light in glass, right? This is clear. So, refractive index of any medium with respect to air is given by speed of light in air upon speed of light in that particular medium. That is glass. If we take an example of glass, then glass. What we see here is that if we are always comparing with air, numerator is always going to be greater than the denominator. So in this case, when we are taking air as the first medium always, then the refractive index of that particular medium will always be greater than 1. Refractive index of that medium will be always greater than 1, and whenever the refractive index is being calculated with respect to air, we call it as absolute refractive index, right? We call it as absolute refractive index. Now suppose if we are comparing between two different materials or two different media, then suppose we are comparing between refractive index of glass and water. So if the light ray is traveling from glass to water, we will write as refractive index of water with respect to glass, right? And this would be equals to velocity of light in glass upon velocity of light in water, right? Suppose if we are calculating refractive index of water with uh, water with respect to glass, glass with respect to water, we will write as V of W upon V of G, right? This will be the thing. So refractive index is basically the comparison between the velocity of light in the first medium with respect to the velocity of light in second medium, right? The reverse of this is also true. How it is true? It is true by following the law of reversibility. What is law of reversibility of light? Law of reversibility of light can be described as, suppose this is the interface and this is the incident ray, this is the incident ray, this is the normal, and let's say this is air, or let's say this is water, and this is glass. Now this is the actual path. Now because the light ray is traveling from water to glass, this is from a rarer medium to a denser medium, light ray will bend towards the normal, right? This is angle of incidence and this is angle of reflection for this case. So if I mark it as angle A and this as angle B, so and I place a mirror at this point in such a way that this is normally incident. When this refracted ray is normally incident, this will retrace its path, right? It will retrace its path. So when the light ray is traveling from water to glass, angle of incidence is A and angle of refraction is B. When the light ray is traveling from glass to water, the angle of incidence is B and angle of refraction is A. So for this case, sine I upon sine R will be equals to sine A upon sine B, which we will write as VA upon V, VW upon VG. And for the case of light ray traveling from glass to water, your sine I upon sine r will be equals to sine b upon sine a, which is equals to v b upon v a, and this we can write it as refractive index of a with respect to b, and this we can write it as refractive index of b with respect to a, right? And what we see is not a and b, this refractive index of refractive index of this is refractive index of water with respect to glass, and this is refractive index of glass with respect to water. So from this calculation, we can say that refractive index of glass with respect to water is reciprocal of refractive index of water with respect to glass, and this is law of reversibility of light. This is law of reversibility of light, right? So this is refractive index of light. So reversibility, principle of reversibility of light is done. Cause of reflection is done, right? So let's now talk about refraction. Let's talk about refraction, refraction through a glass slab. Refraction through a glass slab. Now for refraction through a glass slab, let me select the shape first. The shape is a rectangle. Okay. Let's consider this as a glass slab, right? So suppose a light ray is incident at this surface, right? So here we have air, this is glass, and again we have air. So at this point of incidence, the light ray moving from is moving from a rarer medium to a denser medium. So it would had traveled this path, right? But because it is moving from a rarer medium to a denser medium, what will happen? This will bend towards the normal, and let's say it follows this path and get incident at this point, right? Now, if I draw normal at this point, it would be like this. Now, at this point of incidence, the light ray is moving from a denser medium to a denser to a rarer medium. So it will bend towards the away from the normal. So it will travel outside like this, right? So this is angle of incidence. This is angle of refraction. This angle and this angle will be equal because these two normal are parallel to each other, and this will be transverse. So by the concept of alternating angle, this angle is r, so this also will be r, and this angle will be equals to emergence angle. So here angle of incidence is equals to angle of emergence using Snell's law, right? Using Snell's law. And what we find here is that the light ray which is emerging is actually getting parallelly shifted from its original path, right? That the original path and the emerged ray are parallel to each other, and this parallel shift is known as lateral shift. Lateral shift, right? This is known as lateral shift. And if I write this lateral shift as x, this x is given by the formula x is equals to t sine I into 1 minus cos I upon mu square minus sine square I whole raised to the power of 1 by 2, right? See, this is the formula for lateral shift. Just remember the formula. Derivation is not important. Numerical would also not come, is not that likely to become. It may come, the probability of coming is very less, but this is the formula for lateral shift, right? So whenever a light ray travels or it passes through or get refracted through the glass slab, the emergent ray is parallel to the actual path of the light ray. And what is T over here? T is this distance, that is the thickness of the glass slab. We call it as thickness of the glass slab, right? That is the distance between the one refracting interface to the another refracting surface to the another refracting surface. Right? Distance between these two surfaces is known as the thickness, that is T of the glass slab, right? So whenever your light ray gets refracted to a glass slab, it gets what? It gets parallelly shifted from its original path. How we get I is equals to E? We simply apply Snell's law at this point, that is point A, and at point B. From there, we simply get that I is equals to E, right? Now, this is what is refraction of light through a glass slab. Now, apparent depth and real depth. Now, apparent depth and real depth. So, if suppose this is a container, and to this level it is containing water, here it is water, and there is an object placed over here, right? This is an object placed over here. So we'll draw two light rays passing, getting out of the object, right? This is the first ray. Now because it is normally incident at the interface, it will go undeviated, and the second ray at some angle, this is the angle of this is the incident ray, and if this is normal, this is the angle of incidence. Now the light ray is moving from water to air, that is from a denser medium to rarer medium. It will bend away from the normal, right? This is the refracting angle. Now if I produce this refracted ray backward, this will intersect this incident ray at this point, and this is the point where the image of the object has been formed, right? This is the point where the image of the object has been formed. So if we place our eye over here, right? If we place our eye over here, we will get to see the image of this object over this point, right? So what we find is that we find the image, or we find that the object is placed at this point, so we find the image raised. It has shifted to a height this, right? So if I talk about this distance is the real depth of the object, and this distance is the apparent depth of the object. This is the apparent depth of the object, and this distance is the shift. This distance is the shift, right? This distance is the shift. So again, what is the correlation between the apparent depth and real depth? The relation is refractive index of the denser medium, that is the refractive index of here. For this example, refractive index of water with respect to air will be equals to your real depth upon apparent depth. Real depth upon apparent depth, right? Now, if we talk about shift, shift could be easily calculated from here itself. That shift is real depth minus apparent depth, right? Now, if I divide both the things with apparent depth, right? I have to divide it from here also apparent depth. So this will give you shift is equals to refractive index of water. This can be written as refractive index of water minus 1 into apparent depth, right? Into apparent depth. So if you want to remember this formula, you may remember this formula, or simply this formula will do. That is, the refractive index of the denser medium is equal to the sorry is equal to the real depth upon apparent depth. Right? Real depth upon apparent depth. Right? So now moving forward to your critical angle. Right? Critical Now let's talk about critical angle. Critical angle, right? Now what is critical angle? See, we have seen that whenever a light ray is traveling from a denser medium to a rarer medium, right? Whenever a light ray is traveling from a denser medium to a rarer medium, suppose this is an incident ray and I draw this normal, the light ray is bending away from the normal, right? It is bending away from the normal. This is angle of incidence, and for this angle of incidence, it is angle of refraction following this Snell's law, right? So what we see that if sine I upon sine r is a constant, then as we increase I, r also increases. As we increase I, R also increases. So if I keep on going increasing I, if I keep on increasing this I, this R will also increase, and for a certain value of I, this R will become equals to 90 degree, right? That is, there will be a case while increasing the value of I that for a certain value of I, for a certain value of I, the refracted ray will pass through the interface, and this will be the refracted ray known as the grazing ray, and angle of refraction will be equals to 90 degree. And when this is the case, the angle of incidence I is known as critical angle, denoted by theta c, right? Theta c. So the angle of incidence in the denser medium, for which the angle of refraction in the rarer medium is equals to 90 degree, is known as critical angle. So this will occur only when this will happen only when the light ray is traveling from a denser medium to a rarer medium, right? Now if I further go on increasing, r I beyond critical angle, then what will happen? If this is a rarer medium and this is a denser medium, and the light ray is incident at an angle which is greater than critical angle, for that case the light ray will get reflected, it will get reflected instead of getting refracted, right? The light ray will get reflected instead of getting refracted, and this phenomena is known as total internal reflection, popularly known as TIR, that is total internal reflection, right? So the light ray get totally reflected into the same medium, that is in the denser medium from where it was coming. This is when the light ray is traveling from the denser medium to the rarer medium, and the angle of incidence is greater than the critical angle of that particular pair of medium. And when the angle of incidence is greater than the critical angle for that particular pair of medium, the light ray will get totally reflected into the same medium, and this phenomena will be known as total internal reflection, right? Total internal reflection. So how to calculate this critical angle for a given pair of medium. Again, I'm saying repeatedly, a given pair of medium. Yes, this critical angle is also defined for a pair of medium only, because when we are talking about refraction, there has to be a pair of medium. Each and everything is to be defined for a pair of medium. So, see in this diagram which we have drawn here, where we have shown the critical angle. If I write the Snell's law says that sine I upon sine R is equals to a constant, and that constant is nothing but the refractive index of medium 1, sorry, medium 2 with respect to medium 1. That is refractive index of rarer medium with respect to denser medium here in this case, right? So putting the values, that is, if if I is equals to theta c, if I is equals to theta c, R is equals to 90, so it will become sine 90 and is equals to refractive index of rarer medium with respect to denser, right? So from here what we can say is sine theta c is equals to refractive index of rarer medium with respect to denser, right? And from here itself I can say that 1 upon sine theta c is equals to 1 upon refractive index of rarer medium with respect to denser, which is nothing but equal to refractive index of denser medium with respect to rarer, right? Law principle of reversibility of light. So from here what we finally conclude is we can say that sine, sorry, not sine, we can say that 1 upon sine theta c is equals to sine theta c is equals to refractive index of denser medium with respect to rarer, right? And again making cross multiplication, or you can say reciprocal, what we get sine theta theta c is equals to 1 upon refractive index of denser medium with respect to rarer, and further finally we have theta c is equals to sine inverse of 1 upon refractive index of denser medium with respect to rarer, right? With respect to rarer. So just for an example, suppose a medium M has its refractive index as let's say refractive index as let's say 2, right? Let's say the refractive index of the medium is 2, then theta c will be equals to sine inverse of 1 by 2, which would result as theta c theta c is equals to your 30 degrees, right? For that particular medium, the refractive index will, sorry, critical angle will be theta c. That is when the the rarer medium is air over here, right? The rarer medium is air. Now suppose just for an example, we say that refractive index of glass with respect to water is let's say let me take root 2, right? Root 2, right? Then theta c, that is critical angle, which we formed in the denser medium, that is which will be formed in the glass, will be equals to your sine inverse of 1 by root 2, and therefore your theta c will be equals to 45 degrees. Getting the point, right? So this is how we calculate the critical angle, and this is how the total internal reflection occurs. And because of total internal reflection, mirage formation has been done. Mirage formation occurs, and there are several other phenomena which occurs, which you can see in the book, right? See in the book. Now let's see an example or an application of total internal reflection in case of a prism. Suppose we have a prism like this, right? Now this is 90 degree, and let this be equals to 30 degree, and let this be equals to 60 degree, right? And let the critical angle of the medium of the prism be equals to 42 degrees, right? 42 degrees. Now suppose the light ray is incident at this surface, this refracting surface, and it is normally incident. So what will happen? This light ray will move undeviated, right? Now if I draw the a normal at this point of incidence, this complete angle is 90, this is 90, this is 30. So this, that is the angle between the light ray and this refracting surface, will be equals to, this angle will be equals to 60. Now this is 60, this angle will be equals to 30, and if this is 30, we can say that this angle of incidence is less than critical angle, therefore the light ray will refract outside, right? Refract outside. Now suppose if the case was reversed, that is, this is a prism, this angle is your 60 degree, this angle is 30 degree, right? And this is 90 obviously. Now this light ray, which is normally incident at this refracting surface, passes like this, right? Now if this is 90, this is equals to 30, and if I draw a normal at this point of incident, this angle will be equals to 60, and here also if critical angle is 42 degrees, this angle of incidence is what? Is greater than critical angle. So this light ray will reflect with the same angle of incidence. Now this angle will be equals to how much? This angle will be equals to 60 degree, and if this is 60, this has to be 30, and if this is 30, this is 30, this has to be 120. Now if this is 120, again we will draw angle, we find that this angle is equal to 30, and then it will refract outside, right? So this is how you will be applying your properties of triangle or the geometry over here, and you will see whether the angle of incidence formed inside the prism are less than critical angle or greater than critical angle or equal to critical angle. Accordingly, the reflected ray or refracted ray or the grazing ray will be drawn, right? This is one of the applications of the total internal reflection. This is also application of total internal reflection using prism is also being used in the periscope, right? What is periscope? Periscope is a device which is used to see the objects above some height. So in a periscope, some arrangement is somewhat like this, right? This is a periscope. Here they place a prism, and here also they place a prism. Now object is here. So light ray coming from this object undergo total internal reflection and get reflected to this prism, and from this it get reflected according to total internal reflection and refraction, and it reaches our eye, and we get to see the object, right? So this is because of the total internal reflection in the prism, and prism is so used that the light ray bent by an angle of 90 degree after total internal reflection and refraction through its surface, right? So this is the application of total internal reflection. Now let's see refraction through prism. So here we are going to talk about what? We are going to talk about the refraction through prism. Refraction through prism. Right. Now what is prism? Prism is something like this, a triangle, and then again we have one more triangle. And this triangle and this triangle are joint with the help of three parallelograms, right? One parallelogram is this one, another is this one, and third one is this one, right? It is like if you keep your copy open like this, right? If you keep your copy open like this, right? So this will form a, this is a parallelogram, this is a parallelogram, this is a parallelogram, this will be a triangle, and here it will be a triangle. This is what a prism is, right? So we have this parallelogram as base, this parallelogram as one of the refracting surface, this parallelogram as another of the refracting surface, right? So there are two refracting surfaces. So if I place a prism on a paper, from the top view would be like a triangle. So this will be the prism. This is the first refracting angle, so refracting surface. This is the second refracting surface, and this is the base. And the angle between the two refracting surfaces is known as angle of prism, denoted by capital A. Right? Is known as angle of prism, and is being denoted by capital A. Now let's see how the light ray get refracted through a prism. Now let's draw a prism. We can get a prism from here actually. Now if this is a prism, right, and the light ray is incident at it one of the refracting surface like this, so the normal at the surface would be like this. So since the light ray is traveling from a rarer medium to a denser medium, it actually would have gone like this, right? But because it is moving from a rarer to denser, it will bend towards the normal. So let's say it goes like this. Then again at this point of incidence, if I draw the normal, now the light is traveling from a denser medium to rarer medium, so it will bend away from the normal. So it will go like this, right? So this angle, let us mark it as R1. This angle, let's mark it as R2, right? This is angle of incidence, and this is angle of emergence, E, and this is angle of prism, that is A, right? Then if I produce this emerged ray backward, right? If I produce this emerged ray backward, right, like this, then there is an angle between the actual path and the, there's an angle between the actual path and you see this angle which I am drawing like this angle. There's an angle between the actual path and the emerged ray, and this angle is known as angle of deviation, denoted by delta. What is this? Is angle of deviation, right, denoted by delta, right? So here we have A, R1, R2, I and E, and angle of deviation with us. So there is a relation between angle of deviation I, R1, R2 and E. The relations are as follows, that A is always equals to R1 plus R2, and angle of deviation is equals to I plus E minus A, right? Or you can say angle of deviation is equals to I plus E minus R1 minus R2, right? This is the angle of deviation for this particular case, that is when the refraction is occurring through a prism, right? Again the derivation is not important, directly a formula will be used, right? So del is equals to I, that is angle of deviation is equals to I plus E minus R1 minus R2, or angle of deviation is equals to I, angle of incidence plus angle of emergence minus angle of prism, right? This is how we get. Now, what happens when we go on increasing the angle of incidence? What we find that this angle of deviation first decreases and then falls to a minimum value, and then on further increasing the angle of incidence, this angle of deviation further increases. So, if I draw a graph for angle of, if I draw a graph which is between the angle of deviation and incident angle. Here if I draw I on x-axis and angle of deviation on y-axis, the graph will be somewhat of this shape, right? Now what we can see is that for a particular angle of deviation, for let's say this angle of deviation, if I draw a line, this line would cut the graph on 2 points, that for a given particular angle of deviation, we have two angle of incidences, I1 and let's say it is I2. So if I is equals to I1, then your E will be equals to I2. If I is equals to I2, then your E will be equals to I1. This is the thing. But there is a point in the graph for which value of deviation we have only one angle of incidence I. And this angle of deviation for which we have only one angle of incidence, this angle of deviation is known as angle of minimum deviation, denoted by del m, right? For case of angle of minimum deviation, that is when angle of deviation is del m, for this case your I1 is equals to I2 is equals to I, that is angle of incidence is equals to angle of emergence, and therefore we can say that when it is a case of minimum deviation, when it is a case of minimum deviation, this ray which is inside the prism becomes parallel to the base. It becomes parallel to the base, right? That is only for the case of minimum deviation. The light ray which is inside the prism becomes parallel to the base, right? What else in the case of minimum deviation? For the case of minimum deviation, yeah, for the case of minimum deviation, the refractive index of the medium of the prism is given by the formula your sine a plus del m upon 2 whole upon sine of a by 2, right? Again, the derivation is not that important. Remember the formula, that this is the case, this is the formula for the refractive index of the medium of the prism when the prism is under minimum deviation, that is the light ray which is refracting through the prism is under minimum deviation, right? Now suppose suppose we had the formula deviation is equals to I plus E minus A. This was for any prism, but if angle of prism, that is A, is very small, very small, that is for thin prism, for thin prism, angle of deviation is given by refractive index minus 1 into A. What is refractive index over here is the refractive index of the medium of the prism for the given incident light ray. Now at this note, I want to make a point or a note that whenever we are drawing these light rays for a prism, the light ray used is a monochromatic light. It's not a white light, it's a monochromatic light. Monochromatic light is means single colored light, either yellow light or black, yellow light or red light or blue light, yeah, right? So only a single color is being used for this refraction, and then only this formula, that is del is equal, so it is deviation is equals to mu minus 1 into is valid, right? This is then only it is valid. Now, when we see that for a thin prism, the angle of deviation is dependent on refractive index, dependent on refractive index. Then, if we do further analysis on this point, the first point of analysis is if we write refractive index of any medium is equals to speed of light in air upon speed of light in that particular medium, then using the wave velocity formula, c can be written as lambda into mu, that is wavelength of the light into frequency of the light. Similarly, wavelength of that particular light in that particular medium into frequency of the light, the frequency is not going to change when the light is traveling from one medium to another. This frequency get cancels out. What we get is that refractive index of a given medium is equals to wavelength of the light in air upon wavelength of the light in that particular medium. And what we find is refractive index of a particular medium is inversely proportional to the wavelength of light in that particular medium. What else? That deviation from that above relation itself, we can say is directly proportional to the refractive index. Now, if deviation is directly proportional to the refractive index and refractive index is inversely proportional to the wavelength, we can say from here that deviation is inversely proportional to the wavelength of the light in that particular medium, right? Now, because the deviation depends on wavelength, and if we incident a white light on the prism, what will happen when the light ray is traveling from air to prism? That is for the case of first refracting surface. For the case of first refracting surface, at this refracting surface, what will happen? The white light ray will disperse into its components. That is, white light is composed of different lights of different wavelength and different frequency, and because the different lights are having different wavelength, they will bend by different angle, that is they will deviate with different angle and they will get dispersed, and further while refracting from this second refracting surface, they will further deviate with different angle, and that will result in dispersion of white light into its component, and the dispersion will be something like this, will be something like this. If suppose this is the white light, this is the white light, right? From here it would start dispersing, then further it will get dispersed like this, dispersed like this, right? This will be your light rays. This light ray will be of violet, and this will be of your red, right? Why we have red up? Because the wavelength of red light is much greater than the wavelength of violet light. Now, because deviation is inversely proportional to wavelength, so we can say that because the wavelength of red is very large, therefore its deviation will be least, and because the wavelength of violet is less, so its deviation will be more, right? This is why the violet light comes at bottom and the red light comes at top, and this forms a spectrum which is known as Vibgyor, right? Vibgyor. That is violet, indigo, blue, green, yellow, orange, and then red, right? There are other light rays also which are invisible, right? These lights are visible light. Below this we have infrared, and above this, sorry, below this we have ultraviolet, and above red we have infrared, and these are invisible range of lights, right? So this is what is dispersion of light which is taking place. Now, if there was no prism here, the light ray would have gone like this, right? Now, if the light ray would have gone like this will be this would be angle of deviation of red color, del V, and this would be angle of deviation of violet color, right? This would be angle of deviation of violet color. So what we find that two different colors are deviating with different angles, right? Different angles. So with the help of the formula which we have seen here, that is deviation is equals to mu minus 1 into A, we can write what we can write is wait a minute, we can write is deviation of red color is equals to refractive index of red color for that particular material of prism minus 1 into A, that is angle of prism, and deviation of violet color is equals to refractive index of violet color for that prism minus 1 into A, right? Now, if we again look into the diagram and if we talk about this angle, right? We talk about this part of the angle. This part of the angle is basically your del V minus del R, isn't it? Del V minus del R. So, if we do del V minus del R from here, if we do del V minus del R, it would be equals to your mu V minus 1 into A minus would be equal to del V minus del R will be equals to your mu V minus mu R into R into A, right? Mu V minus mu R into A, right? Now, if I divide both the sides, oh sorry, wait a minute, not dividing both sides. So this quantity is known as your angular deviation. Angular deviation, right? So what is angular deviation? Your angular deviation is given as del V minus del R is equals to mu V minus mu R minus into A, right? This is angular division. Now, if I divide both the side by del Y, right? Del Y. So, what would be del Y? Del Y is your mu Y minus 1 into A, right? So, putting this value here, what we get? Del V minus del R upon del Y is equals to your mu V minus mu R upon mu minus 1, right? Mu minus 1. And this quantity is known as omega, which is your dispersive power. Dispersive, dispersive, dispersive power, right? This is known as dispersive power. And this del y minus del y is known as mean deviation, right? So omega is equals to mu v minus mu r upon mu minus 1, and this is known as dispersive power, right? So right. So this is all we have in your refraction through prism and refraction of light. In this part, I hope most of the things are being made clear to you all. Whatever you have doubt or whatever thing is being missed out, please put it in the comment box. Things will be covered and will be made correct. And what else? This was the second part of ray optics. In the third part of the ray optics, we will be talking about refraction through the spherical surfaces. That is the lens maker formula, and your lens maker formula, refraction of lenses, refraction of lenses, and probably your optical instruments, right? Probably your optical instrument. So this is was all from my side for this part today, right? Thank you.